All right, so I was kind of like thinking, I know that I rewrote my notes and can't to include how to calculate bundles and altitude because once you get into there's so much more to this, and I rewrote it and I put it all in my notes, but I think I'm going to just kind of go past it a little bit. It's interesting for me to note that as far as an A and P goes, I've never seen anything on the tests other than these charts, pretty much. Figure out voltage drop, amps, wire running feet, you're good, take the test, move on, here's your certificate. When you go for your IA, then they throw everything at you. Well, what if it's going to altitude? What if it's this temperature? What if it's in a conduit? What if it's in a bundle? And so all of these things are there, and it's not like you could ignore them, but for some reason, they're not asking you guys to be involved with that at this point. I guess because they figure at that point it's more of a major alteration and such. So if we have time, I'll come back around and go over that stuff because I have so much more to go over. All right, so we know how to basically select wires, but now we have to figure out how to select circuit breakers. Circuit breaker selection. Well, you would think that you just kind of do the calculation, and if it's like 8 amps, just get an 8 amp circuit breaker, but it's not that easy. So according to AC 4313, well, technically 1B, which is the first part, paragraph 11-51, the purpose of a circuit breaker or fuse is to protect what?
The wire.
The wire.
Or the circuit.
Not the component. Wire. Period. Let me see. Electrical wires. I'll just put wires because electrical wires. Wire must be protected. Must be protected as, with a fuse or circuit breaker. I'm going to CB. I'll save time. C world. CB. As close to the bus or power source as possible. AC 4313, table 11-3 can be used as a guide.
-3.
11-3. Oh, here it is. Right. Circuit breakers, CB, circuit breakers are not to be used as what?
Switches.
Switches. If an aircraft uses fuses, that's fun to say. FAR 91. What's FAR 91? Right, general operating flight rules. Who does it apply to mostly?
Pilots.
It's kind of pilots, but as mechanics, we have to know it because we have to make sure the plane complies with all parts. 205 requires the pilot, not you, to carry one spare set of fuses or 3 spare fuses of each kind required.
A spare set, does that mean multiple?
Mm-hmm.
And that a set is 3?
Well, one spare set. So if you had a 5, a 10, a 15, and a 20, you have to carry a.
5, 10, 15, or 20.
What if you had a 1, a 1, a 1, a 1, a 1, and a 5 and a 10? So one spare set of or 3 spare of each kind required.
What? I don't understand why it's like 1 of each or 3 of each.
So if there was like 4 1
So
amps,
if you had 4 1 amps, you only need to carry 3 of them.
and then 3 5s and 3 10s.
Okay. Oh, gotcha.
Well,
They don't require you to carry 1.
or a set, so it'd be like 1 5, 1 10. That's why I'd read it. One set means 1 for each hole, but if they're all the same, then you just need 3.
Because if more than 3 go wrong, you've got bigger
Yeah.
problems.
Yeah,
So like, do some aircraft not use circuit breakers? Or?
that is correct. My Cessna 150 had all fuses.
Would you rather a circuit breaker or a fuse?
I actually changed all the fuses in the circuit breakers on that plane. So starter circuits,
Is that considered a major alteration?
I considered it one. Do not use circuit breaker or fuses. You just go till it melts.
Directly to the battery, right?
No, it actually, you have a fat wire goes from the battery to the, not the bus bar, to the master solenoid. So when you hit the switch, solenoid, then that goes to the bus bar, but that fat wire is right there to the relay. And then there's another relay that sits usually right next to them, especially Cessnas, with sometimes just a metal strap going across it. And then that relay goes wire to the starter.
So there's nothing to protect it. So what? Did it just never have that issue? Just don't overcrank?
I believe the thought is if you're in flight and your engine quits, the last thing you want to deal with is resetting a circuit breaker. You're better off dealing with the other problems that could arise that never seem to. That's my guess.
I guess if you have an engine.
Let's see. Where did this go? Why am I thinking different? I want this. That. Table what? 11-3 can be used as a guide. So if we're using, and circuit breakers to protect the what?
Wire.
Wires. If I'm using an 18 gauge wire, I should have a circuit breaker 10 or a fuse 10. All right. Basis, wire bundles in 135-degree ambient altitudes up to 30,000 feet. Wire bundles of 15 or more wires with wires carrying no more than 20% of the total carrying current. Blah, blah, blah. You should never blah, blah, blah aircraft stuff. So,
Why are the circuit breaker amperages different than the fuse amps?
construction. They're constructed different. One's just going to blow, and the other one has to actually do something, trip. So I don't know. I don't know why 22 is 5 and 5, but when there was 20, go, ooh, whoa, wait a minute. It
Yeah,
better be
that's what I'm saying.
7.5 and a 5. We can't have that. So I do not know. I do not know.
I'd ask.
All right. Switches. Switches must be capable of carrying the load of the wire, obviously. SWITCH. Switches must be able to carry the load of the wire. You can't say that you need a double-aught wire and have this puny little switch that is going to melt the switch. Not going to work. So you have to select a switch based upon the load as well. So once you do the chart that we just did and you figure out the correct wire, now you can figure out the correct circuit breaker, and the next thing to do is figure out the correct switch. So switches are rated to both voltage and current. Are rated to both volts and current. I was watching, it was a very short little video. It was kind of cool. We have a brand new program here at the school that is all brand new Cessna manuals. We bought all the Cessna 100 series manuals. So that includes the engine, props, accessories. Anyway, I was just scrolling through it and it had videos, Cessna videos. I'm like, video? What are they possibly? And one of them was kind of cool, 15, 20 seconds. But it actually showed why they put diodes on solenoids, like the master solenoid and stuff. And I'll kind of work that in the lecture at one point. But what they did is they took a master switch. So when you get in an aircraft, everything's off, it's dead. You hit the master switch, which opens a relay, as I said solenoid, but a relay, and which brings then power into the bus and the aircraft is on. Well, when you click off that, then you're switching that off. Well, in a relay or solenoid, you are creating voltage when things move across those wires, and we'll get into that. But anyway, that creates a voltage spike. They drilled a hole in the side of a master switch, and they showed how bad it arcs without the diode. And so you have to consider that when you have a lot of voltage across a switch, when you go to turn it off, it arcs. And every time it arcs, you're kind of destroying the life of the switch. So you don't want that. See, the nominal rating. Nominal rating of the switch is printed. Nominal rating is printed on the switch.
So that diode completely stops that arcing, or
It sends the arc spike somewhere to ground. The max current is that the switch can continuously handle with contacts closed. Yeah, nominal rating. That's the max current. All right. So some loads. That's a bad sentence. Have a higher current draw at startup. So the switch needs to be derated, not berated. That's a different thing. You suck, you switch. Derated for these applications. All right, so what I'm saying, some things have, just what I just wrote, some things draw a lot of current until they get going. So there's an initial inrush of current, and then it settles back down. Where have you seen this?
On the motors.
Motors. Motors do that. Believe it or not, incandescent lights, if you can still buy one, they do that. Until that filament heats up, it's got a different resistance. Once it heats up, it draws a lower current. So we typically design the circuit and the wires not for this sudden influx, but more of what is the continuous load. But at the same time, the switch has to handle that load when you flick it on. The circuit breaker won't pop, so that's why we don't have to worry about the circuit breaker. The wire only handled it for a fraction of a second, but the switch wasn't rated for it, so you have to derate the switch. So some things that this applies to, I just said incandescent lights. What's incandescent?
These ones? Oh,
These are fluorescent.
Oh yeah, like just.
Your
like
old-timey
controller.
gets really hot.
Yeah.
Yeah. Remember those. Motors. Or any inductive circuit. What the heck is an inductive circuit? Well, the root word is inductor. What is an inductor? Inductor is a coil. So any circuit that has a coil in it. What has coils in it? Relays, solenoids. Capacitor is the opposite. It is the literal opposite. All right. There was a note in there. Do not use AC derated switches in DC circuits. In DC circuits. Sometimes switches are printed. It's not that they're AC switches or DC switches. It's just that they're rated in one or the other.
So, what is derating?
I'm going to show you what derating is. So thank you for asking with that. That was see, he's my guy. Perfect segue. So table 11-4. I should answer that question though before I do that. So derating is like, they do that with motors a lot. So a manufacturer builds a motor and it's 300 horsepower, but it's going to go in this crappy car and they want the same motor, so they have to derate it. So they do something to it, so now it only puts out 250 horsepower.
But it will last longer doing so too, correct?
Well, now you're getting off the topic, but in theory, yes. But I don't know, you're going to change the oil, not change the oil. So I don't know what they do. They put a restrictor plate on it. They, detune the timing, do something to make it so it's not as good. But it's like, it's the same motor. So the computer chip. So you go out and buy the computer chip, swap the computer chip. Now you get the horsepower. All right. So same thing. They just take something that's good and say, well, it's not as good as you think it is. We're going to pretend like it's not, but it's really good. So table 11-4. Where am I? Table 11-4 shows derating chart. Shows derating chart.
Is that in AC 4313 too?
Yes, not 2, but AC 4313-1B. Derating chart. 11-4, derating chart. All right, switches used in electrical motor circuit must be derated by a factor. Have you seen like that? That didn't make sense. Okay, example. We have a 28-volt lamp, that's a light bulb, that draws 5 amps. 5 amps. So what are we going to do with that?
Derate it by a factor of 8.
All right, so we find the 28-volt lamp right there has a derating factor of 8. So we had 5 amps times 8 equals 40. So you better get a 40 amp switch.
Damn. That's a lot. More. I mean, what would the normal switch? I mean, I guess that's. What would, if you didn't have to derate it? Just go 5 amp.
Then you need a 5 amp switch.
You're telling me I could have ran my motor straight from the switch.
Get a what?
Run the motor straight from the switch. You get a big enough switch.
Just get big. Well, you can, yeah. You can run anything without a relay. Just get a big ass switch. What's the largest motor at 28 volt? 28 volt, 10 amp switch can handle. What's the largest motor? Which is a weird thing to say. Well, I've got a 28 volt switch, says 10 amps on it. Which motor should I use?
3 amp.
Yeah, well,
So what's my derating factor for a motor on a 28 volt? 3. So I have a derating factor of 3. So what are we going to do?
10 by 3 amps by 3.
10 divided by 3 equals
3.33.
3.33 amps. Yeah.
Why would you divide it instead of multiply it?
Because I asked, what is the motor that you could use? It was a backwards way of doing it. Nobody would ever do that. That's what I just said. Look, I found a switch that says 28 volts, 10 amps on it. I wonder what motor I could run off of this.
Oh.
So it's like you bought the switch and now you're trying to figure out what motor to buy next. If you do that, you probably shouldn't be designing aircraft. How many watts is that? About 92, 93 amps? Okay. Sorry, 93.3 watts. Okay. 28 horsepower motor. All right, do you understand how to derate stuff?
Yep.
Okay, it's on the test.
Can you do another, like, example?
Do what?
Can you do another example, like, I don't know, how do you know when to multiply and when to divide?
How do I know when to multiply or when to divide? It's the question that's being asked. So, in example 1, I said I have a 28 volt lamp that draws 5 amps. What switch do I need? Got it? What switch do I need? So I took the 28 volt lamp and I found the derating factor, which is?
8.
Got it? 8? Okay. So I multiplied that by 8 because I need to figure out what? The switch. Question number 2, I said, I went to the store because I'm an idiot and I bought a switch. And I put the switch in first. Then I said, what can the switch run? Right? So I have to divide it. Then I also said, really, if you get into a situation where you buy the switch first and then try and decide what it's going to run, you probably shouldn't be designing aircraft because it doesn't work that way. But it was an example to show how the chart works both ways. So that is how you determine whether it's division or multiplication. So to do another one that would be more realistic, let's see, you've got in the lab class there a motor that I think it says it's labeled as, I think it's a 4 amp motor, yeah? And it's 28 volts. What size switch would you need to run that motor that you are doing in lab?
12 amp switch.
The switch needs to say
12 amp, 28 volt.
12 amp. Why 12 amps? One, because we bought the switch after we figured out the load. So here we have a motor that must run. We figured out how many horsepower the motor is. We designed it correctly. We get to the end. We figured out the wire, everything else, what size switch. 28 volts, 28 volt motor has a derating factor of
3.
So you multiply that times 3 and the switch should be able to handle
12 amps.
should be able to handle 12 amps. What's it going to run at most of the time?
4.
4, but it just starts up at 12. So, all right. You do have a couple of little solenoids, relays, solenoids that you're also running. You only run one at a time. So, what size switch do you need to run that little relay? Well, you have a circuit breaker that's 2 amps, so I'm going to assume that you're not running more than 2 amps. So what size switch should you be using on that circuit that you're doing?
8.
Well, what'd you do? What's my derating factor for
28 volt relay is 4.
The 28 volts would be
28 volt inductive relay or solenoid is 4. So multiply that times 4. It should be able to handle 8 amps. But at the same time, you're also running a light bulb in there, right? So that light bulb, I don't know how many amps it draws, but it's 2 amp circuit breaker, so we want to be safe. 2 amp circuit breaker. What's the derating factor for the lamp?
8.
8. So times 8. So the switch should be able to handle.
16.
So would I set it up for 8 or 16 or 12?
16.
Why not 12? Because it's less.
Always running that.
So if this were correct, which it's not because the lamp doesn't draw 2 amps, then the lamp, the switch to run the lamp is actually going to have to be more than the motor. So if we really wanted to think it through, we should use the relay to run the lamps and run the motor right through the switch. So
So is this derating also applicable to a relay if you're trying to find the correct size relay?
absolutely, look at the chart.
Okay.
Works for lamps, any inductive circuit such as a relay solenoid, resistive heaters. Where would we find resistive heaters?
Heater,
Yeah, captain seat heaters. A motor that is not a motor that runs on gasoline.
Sorry, instead of using, so this is to find a switch for the correct amperage for a switch. I'm saying for like the correct amperage for a relay, the sizing of a relay.
Oh, sizing of a relay. How big does it? I think it's printed
This is
on there.
still pretty much it.
Yeah, because just bars that close.
Okay.
So
At what,
I think they'll give you the rating on the relay.
at what point would you say, how many amps is like the maximum, like a realistic switch in an airplane would be able to handle, before you have to then put a relay in the system?
I don't really know the answer to that. It's kind of an electrical engineering thing, how they want to run it. It's going to depend upon. So the way I would do that is I would find the switch, what it looks like, how big it is, how much room I have, and if it doesn't make sense, then I'm going relay.
You know, so you kind of do it like, almost aesthetically, or like how
Yeah,
you feel.
because if you think about, most aircraft that I know of that have incandescent landing lights, they're 100 watts or more, and they just use little tiny rocker switches. I mean, my rocker switch for my landing lights are so small, but there's also service instructions that says you change them every couple hundred hours. So, shoot. Okay, so derating factor, switch material. So you even get to go down into selecting of contact materials. So if you have a supply volt 30 and the current was 1, you would want to use silver. If it's a half an amp, you can use gold or silver. If it's 0.01 amp, it's gold or bifurcated. So it just shows the acceptable switch material. The lower the voltage, and the lower amp, which is funny, the lower we go down this way and the more we go this way, the more expensive the switch becomes. Why is that? The smaller the current, the smaller the voltage, the more expensive it becomes. Everything we talked about recently has been getting bigger and bigger switches, and now suddenly it's like, why is the little one so expensive?
Do you need to have such a high sensitivity for picking up current that?
You're close. Wouldn't be sensitivity.
It would be resistance. It would be
Resistance. What is resistance?
it's
What is resistance going to manifest itself as?
Voltage drop.
voltage.
Voltage drop. So if we're only using 0.01 milliamp and less than a volt, boy, you're not allowed a lot of voltage drop across that. You're playing with 30 volts, it'll burn in. It'll work itself out. That's one of our favorite sayings, It'll either wear in or wear out. Don't worry about it. All right.
Trim it out.
So we're good with that. We're good with derating. We've covered selection of circuit breakers. We did not cover that. We covered continuous versus intermittent loads. We covered how to find the right wires. Now we shall talk about proper wire ends. I have to throw out a choice for you guys, since it's your life too. I don't have a lot, but it's normally I would stop right about now and start doing kind of more of an overview, go back over everything we covered. But if I did that now, I'd be leaving stuff off that's important. So I don't want to do that. So that means that you won't be ready for a test tomorrow, because it was a short week. So I propose that we take the test Monday when you get here. And that doesn't put us now another day late next week. So Monday when you show up, lab time, walk in here, take the test. As soon as you're done with the test, go across the street, get to work.
And then we talk about the answers when we come back in for lecture.
Yep, then we'll do the answers real quick. We'll come back in from lecture. So for some of you, you'll miss like 10 minutes of lab. So Yeah, that work for you guys?
Yeah.
Okay, so we can carry on then. So then we'll have lecture tomorrow, too. So, all right, table 11.4 shows the derating chart. We got all that. We're good with derating. Everybody's good with derating?
Yes.
Okay. Proper wire ends. So 12. Use proper wire ends. Oh, I don't like this one. It just makes my life more difficult when you're actually out there working. You don't have the right end and you can't run to the store and buy them because the store does not have mil-spec wire ends. So we use mil-spec wire ends. Mil-spec terminal lugs. Oops. I also call them ends, terminal ends. Ends are tinted a color. A color code that corresponds to the wire size. Or combination of wires. So what I'm talking about, it's not that. Oh yeah, those two. Here we go. So our terminal ends. We have terminal ends. We have butt connectors. We have the different colors: red, blue, yellow, and nothing. Let's see. Yeah. The idea is when we, this is funny, in automotive, we crimp it right here. But in aviation, it double crimps. It crimps once on the insulation and once on the barrel. So you're crimping onto that Teflon insulation. It's really tough to pull these things apart. And that's the whole idea, is tough to pull apart. Huh?
Why don't we do that everywhere then?
Because these crimpers cost a lot of frickin' money. And they're calibrated. Now, I will admit that most people don't use calibrated aircraft crimpers, but you look them up online. I mean, I want to say they're in the hundreds of dollars range.
They're like $800 or $900 sometimes.
Yeah.
I got a free pair.
Yeah. I don't know if I have this in. I do. It's like the next thing I'm going to write here is you can put them, and this is a Q&A question. It's just a known fact in aviation. These are terminal ends or lugs here. The most you can stack onto any one of these is 4. So these are a phenolic block. It's like a plastic, and a terminal block is what you're called. And so, like this could be like a bus bar. Like this could be the power in right here. This could be battery. This could be generator. And then these are the loads. It's very small for that, but it's as an example. All right, so we got red.
So what about a switch? What about a switch if you have like a double pull, double throw? And you
I
have
stick with 4. I never go more than 4 things on a.
on either terminal.
Yep. That's my personal rule because that's the only rule that I'm aware of, and so I never violate that one. It's 4 to a plug.
So you go all in the same like ring terminal, crimp the ring terminal around all 4 wires,
Oh, how many?
or you
I don't like to do that.
do like 4 different ring terminals.
I would do. Depends on the application, but I can't think of an application where he's talking about kind of cheating on this a little bit. Could you just double the wires up here, put 4 wires into this terminal end, use a yellow one, put 4 small wires in, crimp them, there's 1. And then do that like 4 more times, so you have 16.
No, I was more thinking about like the switch and like having space, like you have 2 indicator lights and a tail light. So you only have 2, double pull, double throw. You only have 2.
Okay, so and that's what I was thinking. What's on any given switch? We don't stack a lot of stuff on a switch, right? So you're just not gonna do that kind of thing. Like for example, if I have a radio master and I flip that radio master on, and that's supposed to operate 5 different radios, then you're gonna make that go to a mini bus bar that looks like this, where each radio goes to it. So you just don't stack stuff up like that in aircraft. You talk about nav lights where there's 3. Well, now it's 3. That's fine. So one switch operates 3 lights. And that would be normal. So you can put 3 ends on one and the power coming in and 3 on the other. But it's just, I've never seen a need to go more than 4. And if you do it something like this, because now you're getting into bigger loads. Okay, so color codes. Red is 22 to 16 gauge. 22 to 16 gauge. So if you have a 22 gauge or 16 gauge wire, you're going to use the red. Blue. Blue is 16 to 14. I don't know, if you have a 16 gauge, what are you going to use? The red or the blue? Yeah, sure. So whichever one you have. Yellow is 12 to 10 gauge. And then beyond that, they do not have sleeves on them. The other thing that is worth noting is these colors. Can you see that they're translucent? You can see through them. In automotive, you can't. And that's a big difference between that and the mil spec. And you can also see, if I enlarge that right there, see how it's crimped right here? Yeah, so it's got the double crimp here, crimp there, crimps once onto the insulation. And what color are all those wires?
White.
Yeah.
Varying thicknesses.
All right, so let me see. Max of how many?
4.
4 terminal ends. Per stud, or 4 grounds per screw. Sometimes when you look under an instrument panel, you have all these radios and lights and all these different things, and they come to a ground. They'll take like this huge bundle and go right up to 1 screw. It's 4 per screw. There is a note in here, and I think I put it in here because it might be a Q&A. Check terminal strips. To make sure studs do not rotate. That's these studs right here. These studs should not rotate. They're actually bolts usually that go the other way. Yes?
If we did see where somebody took a huge bundle of wires and slapped it onto one stud, would we try and like spread it out across them?
I would.
Or drill a new one?
Drill a new one. Find a different spot.
Okay.
Yeah.
Put it somewhere else.
Somewhere else. Right? We get the ground loop thing, right? Yeah. Okay. Use the proper crimping technique. I'm going to show you a video. Try not to get distracted that the absolute coolest thing about the video, and I hate to say this, is her incredible fingernails. See?